All right, now let's talk about some different types of IP addresses. We already had an overview of IP addresses, what they are, what they look like, blah, blah, blah. Now let's talk about some of the different types of IP addresses and what they can be used for. So, in the olden days, when we, meaning me and the other people who invented IP addressing, we had all of these addresses. We had 32 bits of addresses, and that was 4 billion different addresses. And we thought, you know what? 4 billion's a lot. So let's find some different ways to chop them up. And the first thing that they did was divide these networks into different classes. And they divided them into different classes based on that starting number. So the first number for 1 through 126, the first 126 networks, were called Class A networks. And they had a subnet mask of 255.0.0.0, which left 24 bits for hosts and 8 bits. The first 8 bits were for that network ID. So really, we had 126 different networks with 24 bits of hosts. And 24 bits means 2 to the 24th power hosts, which is around 16 million. So these were networks that were large enough to hold 16 million different devices. Those were huge. Those were very huge networks. And those were handed out to different companies. Apple got one. Let's see, who else? Ford got one. A bunch of the large companies. I'm sure the military had a few. The government had some. But a lot of large organizations were given these networks of 16 million hosts to use. The Class B addresses were 128 through 191. Now, if you'll notice, Class A ends at 126, Class B ends at 128, because the 127 network, 127, you may be familiar with it because 127.0.0.1 is the loopback or the local host address by default on your computer. So 127.0.0.1 refers to your own computer, and the entire 127 network was saved, reserved for that loopback or different addresses for addressing your own computer. And you can actually use different addresses for addressing your own computer if you'd like to. But then we have 128 to 191, which is that Class B addresses. And that had a subnet mask of 255.255, which means that within those, I'm not going to do the math, but 191 minus 128. Within those networks, we could split those up and create different subnets using that second digit of the IP address. For example, 128.1 would be a different network than 128.2 because the subnet mask covers the first two digits in that IP address. So 128.1, 128.2, 128.255, those are all separate subnets. Unlike 10.1, 10.2 under this class full addresses, where each of those would be part of that 10.0.0.0 network. So then, and that went all the way up to 120 or 191, and those were larger networks. We still have 16 bits for hosts, which is around 65,000 hosts per network, which is still a fairly large network, but not nearly as large as the Class A's. So after the Class B, we have the Class C, 192 to 223, which are much smaller networks. They have a lot fewer bits for the host ID, but we have 3 octets for the network ID. So inside of 192, we can create 192.0.1, 192.0.2.0, 192.0.3.0, 192.20.5.0, and all of those would be separate networks. And the last 8 bits are all that we have for the network ID. For the last 8 bits are all that we have for the host ID. Meaning we can only have around 255 hosts, or 2 to the 8th power. Much smaller networks, still useful, 250 computers, that's great for a home network, and a lot of businesses, a lot of small businesses don't need more than 250 computers on a network. The next range of addresses is reserved for multicast, and that's something we'll talk about later. It's kind of a internet subscription service where you can subscribe to a broadcast and that can get sent out to multiple computers at once. Pretty handy. But 224 to 239 is used for that. And then the last chunk, 240 to 255, is reserved for experimental use. So they saved that just in case, and I don't know what it's ever been used for, but it's there. The issue is we don't need IP blocks of 16 million addresses. Nobody even wants a network with 16 million computers. One network with 16 million computers would basically be shut down and completely consumed by the broadcast traffic of those 16 million computers talking to each other and coordinating communication. So that's not ideal. But we still want to be able to use those early networks. And so what they needed to do was create a way to use an arbitrary subnet mask. So remember class full routing. Each of these classes of IP addresses had a specific given subnet mask. And that was unchangeable. You couldn't change the subnet mask. If you had a 10.0.0.0 network, you were stuck with it. And you could not subdivide that network into anything smaller. With classless routing, we're allowed to use an arbitrary subnet mask. So we can take that 10.0.0.0 network and chop it up into smaller pieces by making a longer subnet mask and creating different networks. So then we can create 10.0.0.0 and 10.1.0.0 and 10.5.0.0, etc. And that's awesome as long as those networks don't overlap. And this completely saved the internet because we don't have enough IP addresses as it is, even now. Remember, I said 4 billion. If 7 billion people on Earth want to connect to the internet, we're going to need a lot more than 4 billion IP addresses. So we're kind of in trouble. That's why IPv6 is coming around. But this at least postponed that by allowing us to chop those large networks into smaller networks, meaning that Apple or Ford didn't need to keep all those 16 million IP addresses for themselves. They could keep what they needed and then let other people use the other subnets or other chunks of that Class A network. Another type of IP address, and a very important type of IP address, is the private address. So, within each class of addresses, there is a chunk of networks, a chunk of IP addresses that cannot be used on the internet. And this is important. So, under Class A, anything that starts with a 10.0.0, anything that starts with a 10 is a private address. And what that means is a 10.anything can't be allowed on the internet. Same under B, we have 172.16 through 172.31. So 172.17, 172.30, all of those are private addresses that can't be used on the internet. Finally, under Class C, you'll see probably one that's familiar to you, 192.168.0 through 192.168.255. This is what's most commonly used on home routers. So your router probably sets you up with a 192.168.0.1, or well, it probably sets itself up with .1 and .2, .3, .4, .5 for your computers. So remember, private addresses cannot be used on the internet. They are fantastic for internal networks. They're great because you don't have to purchase public IP addresses to create a local network. But through the magic of network address translation and or port address translation, you're still able to access the internet using these private addresses. Now let me explain what that means. So inside of my local network, I have a PC that's 10.0.1.2, and a PC that's 10.0.1.3, and a laptop that's 10.0.1.200. And all of those are on the same network. They're on the internal network that has that 10 network address. Oh, it looks like I have a subnet mask here of 255.255.255. So actually, in this case, my network address is 10.0.1.0. The router gave itself the .1 address. Then we have .2, .3, .200, and .201 for my ancient PDA. So inside of my local network, my devices have that IP address. Remember, my router has to have an address on each network that it's connected to. So on the inside, it's 10.0.1.1. On the outside, it's 68.266.49.236. And it has its subnet mask it's subnet mask, and it has a default gateway. When we talk about routing, I'll explain what that means, but that tells it how to get out. So how to send traffic outside of that network. So on the inside, the router's 10.0.1.1. On the outside, it's 68.226.49.236. What this is magically able to do, what this device is able to do, this router, it's able to translate 10.0.1.2, 10.0.1.3, 10.0.1.200, and basically pretend that everything that you send it is coming from it. So to the outside world, your IP address is 68.226.49.236. Because that's a public IP address that can be used on the internet. And the router takes your traffic, translates it, and says, you know what? Instead of being from 10.0.1.2, I'm going to send this from 68.226.49.236 because I can use that on the internet. And it goes out, and then it comes back, and then it translates it back to send it back to you. So check this out for yourself. Check your IP address with ipconfig. You might have already done this, or ifconfig if you're on a Mac. Now, after you've checked that, look at your IP address. Make sure you're almost definitely going to have a private address. Now, open up Google or Bing or whatever. You can go to, what is my IP address? Or you can ask Google, what is my IP address? Or you can go to this URL, myip.is, and get your IP address. And that is the IP address that Google has for you. Are they the same? No. They're almost definitely not. If you're at home, definitely not. If you're at the office, maybe. Because some offices will have public IP addresses for all their employees. But most likely you're going to have a private address, one of those private addresses in ipconfig, and a different public address when you ask Google. Because your router is doing that translation, because your private address can't be on the outside network, but its public address can. The router's public address can. So network address translation, typically when we talk about network address translation on its own, we're referring to matching a single external IP address with a single internal IP address. And that looks a lot like this. So on the outside of this network, we have 137.45.25.25. And on the inside, we have 10.0.1.1. And then on the outside, we have 137.45.25.100. And on the inside, we have 10.0.1.2. Those are NAT. Those are one-to-one records, meaning that if someone from the outside sends traffic to 137.45.25.25, that's going to get translated when it gets to the router and then get sent to 10.0.1.1. And the same goes for the .100. It'll get translated and sent to 10.0.1.2. So this is fine. This is very useful. It's good for obscuring that local network layout and bridging different networks with different addressing schemes. But the real magic happens with what's called port address translation. And a lot of times you're going to see this called NAT. It might be called NAT overloading. So I'm not going to get picky about whether you call it NAT or whether you call it PAT. But the important thing to learn is that this is absolutely awesome, because what it can do, rather than what standard NAT does, which is a one-to-one map, this can map a single external address with multiple internal addresses. So outside your network, your router has a single external address. Inside your network, you've got 30 devices or 10 devices, whatever, right? So you can send traffic, and all of your traffic gets sent to your router to get outside your network, and all of those internal addresses get translated into a single external address. And the way that, a single external address. And the way that happens goes something like this. So we'll start at that top with TCP 62659 destination 80. If you're sending something to Amazon.com, if you're sending a packet to Amazon.com on port 80, your computer is going to create a packet, right? A TCP segment that gets packed into packet, etc. That's going to have a destination port of port 80 and a source port of 62659, because it just randomly picks that source port. And then a source IP of my IP address in this case, if I'm computer 10.0.1.3. And so my source IP address is 10.0.1.3. My destination IP address is Amazon's IP address. And I'm going to send that out. And that goes to the router in the middle there. And what the router does is it takes that packet with source port 62659, destination port 80, source 10.0.1.3, etc., and it changes it. And it takes off the segment information, and it takes off the port information, and it creates its own. And the destination port stays the same. The destination IP address stays the same, but the source port and the source IP address change, because the source IP address is now the router's IP address, and the source port is a new port, another random port from that dynamic port range, 61022 in this case. And then what the router does, it takes 61022 and it adds a little map, and it says when traffic comes back, and you can see the map here just above the router, when traffic comes back for port 61022, which is the source port on the packet we sent to Amazon, then I'm going to translate that on the inside to 10.0.1.3 port 62659, which is the original port that your computer used when it created that packet. So your computer, when it sent that packet on 62659, it started listening for traffic to come back on 62659. So it's going to be listening this whole time while we talk about what happens next. So this packet goes to Amazon. Amazon receives it with a source port of 61022, source destination port 80, source IP address 137.45.25.25, destination Amazon. Amazon gets it. It says, okay, I'm going to respond, and it sends back. And it sends back on port 61022 because that's the one it received on. And again, and it sends it, the destination IP address there is the router. So as far as Amazon's concerned, your router's talking to it. And if 10 different computers are talking to it, it's going to get inside your network, it's going to get 10 different requests from 137.45.25.25, the router's IP address. And Amazon doesn't care. So it takes that packet, sends one back. The router now receives that packet on 61022, destination 137.45.25.25, and it's going to use that map that it has to translate it, strip off that port and IP address information again, and create a new packet with source port 80, destination port 62659, because that's where my computer is listening. That's the port that my computer opened to create this. Source IP address of 54.25.3 or 54.239, etc., Amazon's IP address, and the destination IP address of 10.0.1.3. So all the traffic happening inside my local network can use those private addresses. But when we get outside, then we have to use the public address, and that's where the router comes in. So PAT, port address translation, is awesome for home networks. It's awesome for corporate internet connected networks. It's awesome for corporate non-internet connected networks. If you have a network, you're probably going to be using private IP addresses and some sort of port address translation if you want to get to the internet. And you save IP addresses this way, because my house, while I have 14 different devices that are connected to the internet, my house only needs a single public IP address, which saves us those public IP addresses that are such a scarce resource. We're running out of them. There were only maybe 4 billion to begin with, and they're gone. So I can use one single public IP address at my house to communicate on my 10 different devices, rather than using 10 of them, one for each device. And it also provides just a tiny bit of security. It's a very, very basic firewall, because what we have here is if a bad guy wants to get in, and the router has this map, right? The router keeps track of what traffic's coming in and out, and it says, okay, if anything comes in on 61022, I'm going to translate that and send it back to this PC. Well, if the bad guy sends traffic to port 22, the router says, well, I'm not listening on port 22. I've got nothing. I'm not listening. And even if you have 20 different devices inside your network that are listening on port 22, by default, that router is not going to send anything into the network unless you tell it to. So the bad guy, when he tries to get in on port 22, that SSH port, he's going to get cut off. If you do want traffic to come in on port 22, you're going to want to set up something called port forwarding. And you can log into your router and there's a tab there probably for port forwarding. If you want remote access to your internal stuff, if you want to always be able to get into your computer on port 22 SSH, or if you want to run a web server at your home on port 80, then you need to do port forwarding. And what you do is basically manually create that map inside the router. And you're saying if any traffic comes in on port 22, send it to 10.0.1.3 on port 22. And you can translate that. And it'll take an external port and translate that into an internal port. That's port forwarding. So if we've set up port forwarding, created the second line there in the map, port 22 goes to 10.0.1.4, port 22. Then when the good guy tries to get in and says, port 22, here I come, then that's going to get translated to port 22 on the inside. Now, an important thing to note, this lets the good guy in. It also lets the bad guy in. So now that we have this port forwarding rule, anybody who wants to can come in on port 22. And that is the different types of IP addresses and network address translation and port address translation in a nutshell.